For now, we are pleased to welcome our second keynote speaker, Cole Nielsen, founder and CTO of Orbital Composites, and he successfully completed advanced composite research project on continuous fiber robotic AM with various materials for many applications. Today, he will present thermoplastic composites and the winds of change. Ladies and gentlemen, please welcome him.
Hi, everybody. Thank you. I have a second computer I'd like to share my screen with. The name for that profile is Orbital Cole. If we can enable that, that would be helpful. I need to be made a panelist. So Orbital Composites was founded about 7 years ago. The objective for Orbital was actually to build sort of very fast drone and helicopter technology. And we are quite excited to work on and with robots every day. Yes, I'd like to share the screen, but I have a separate, I just raised my hand on the other computer. If we could go ahead and make that one a panelist as well, I can share the screen. Thank you. So Orbital has spent the past few years figuring out how to 3D print continuous carbon fibers, thermoplastics, thermoset materials. There's a lot of work that goes into the actual end effectors, and as well the fiber systems, the control systems, in order to be able to make that possible. Right, so the slides will, unless someone else would like to share the slides, my second account needs to be enabled. Okay. So Orbital is currently spending a lot of its time building robot systems of various sizes with Department of Energy. We recently, thank you very much. There we go. We've recently been funded by the Department of Energy to go ahead and 3D print wind turbine blades. And this is really the beginning of quite a wonderful dream that I'd like to share with you all. There we go. There we go. Okay, here we are. All right. So this is a drone video that we took in Denmark, and really what we think is going to happen is that the the wind turbine industry is going to be a critical driver to see change in the way that composites are deployed around the world and in various contexts, everywhere really. So we think that we're not really going to see adoption by automotive until we've really figured out how to have automated sort of additive production of continuous fiber composites at the same dollars per pound you would find in a car. It's actually kind of interesting that wind turbine blades, big ones, dollars per kilogram, and automobiles, dollars per kilogram, is actually a very similar number. Those two are much closer together than the cost difference between airplanes and helicopters versus wind turbine blades, even though the structures are very similar. So therefore, the advances that we find in the next generation of wind turbine technology is going to be the advances that we'll see the world over. And as we begin to shift away from whatever it is today, about 90% thermoset matrices. The last presentation by MIT was fantastic, by the way. I love that. That was great. So just a couple quick facts here. Wind turbine blades today are the monopoly consumer of continuous carbon fibers. So you're like 55% plus. So it might be pitch-based fiber, it might be pan-based fiber. but the vast majority of carbon around the world is going specifically there. So any technological change is going to have a lot of leverage on the rest of the continuous fiber industry. And all that carbon fiber is placed primarily by hand. It's not done by robot. The wind power market is actually growing. Even with that sort of market share, it stands to gain more market share. In the next decade, offshore wind in the US is supposed to go from 0 to over 30 gigawatts. That's a lot of towers, and that's just offshore. That's not the rest of just natural market growth. So huge installations coming. And what's really interesting is that the land-based turbines, with all turbines, the bigger the radius of the rotors, then the more efficient that system becomes. So, but we're kind of stuck because we have bridges and roads that were designed a long time ago, and they, in the United States, actually don't allow for wind turbine blades of much over 60 meters to be moved around freely on the back of trucks and so forth. So there's a huge tyranny in mobility. So if we can mobilize the manufacturing process, then we don't have to struggle with moving very large blades. And then when we look at, I think today global supply for blades, or global demand, is like 9,000 blades per year or so. So, that's a lot, and it's also a tremendous amount of waste. So if you look at a growing market that's also consuming most carbon fiber, if that evolves to go along with the rest of the green evolution and technology, then it seems that a transition away from thermostats over to thermoplastics is really sort of the best way to go. That means that, from my perspective, the wind turbine blade market continuing to grow will actually be the leading indicator of the transition from thermoset to thermoplastic blades. So then our conclusion at Orbital here is that mobile manufacturing, continuous fiber, thermoplastic materials, 3D printed by robots will actually become the dominant composites manufacturing technology as we move forward. So let's go ahead and look at what that would, let's take a look. Okay, so here, just trying to get a sense of scale to these issues. The Saturn V rocket that took the Apollo astronauts to the moon is actually the same size as the LM wind turbine blades today. SpaceX Starship, same size. That's kind of interesting that we're at this 100-meter length scale with about a 10-meter diameter, and we have sort of the apex of aerospace engineering being rocketry, starting to have a lot in common with the wind turbine industry, actually. So some of the shuttle solid rocket boosters are actually carbon fiber. So composite rockets are not strange. I'm just pointing out some similarities. So some of the other similarities are that moving those behemoth structures around was a problem in the 60s and 70s, just as it is today. So the blades have same size, the same mobility problem as these giant rockets. So we've turned to barges, which works for offshore wind. But wind turbine blades are not going to go into airplanes. That's just not going to be cost effective. So ground transportation and oceanic transportation for the manufacturing system starts to get interesting when you compare with the scale of what you're seeing on screen. So in the aerospace industry, there's actually a really important change that's going on right now. And it's the evolution of a new technology that we call OSAM, or on-orbit assembly, servicing, and manufacturing. And so the idea is very simple. You wouldn't decorate your Christmas tree and then put it in your car, struggle through a 12-minute car crash and expect everything to work on the other side. But when you take a satellite, fold it up into tiny little pieces, stuff it into a rocket, and vibrate it for all the way 12 minutes, which is basically a car crash, and deploy that satellite on orbit, you've spent most of your engineering time actually designing for 12 minutes of launch, not 20 years of operations. And we're coming to a point where segmented blades, as an example, are a way to mobilize that system, but we're spending our time on actually, we're spending a lot of engineering effort on mobilizing a very large system as opposed to building it after it's at the correct location. So the most extreme example of this would be 3D printing the wind turbine blade on the actual tower, which is kind of what you would do in orbit. So it's very interesting that this technology is evolving right now, because we start to see that there's a technology overlap in that the leading edge of aerospace composites is going thermoplastic, it's going continuous fiber, it's going additive, which is a lot of the way that the wind turbine industry, we feel, is going to change as well. So this is where the imagination can become free, I think. And when you have a new kind of manufacturing system, you can bring science fiction futures to today. So here is some of the development we've been working on. This is a sort of robotic targeting and collision avoidance. I don't want to call it an AI, but it's basically a machine learning swarming solution set that enables us to get multiple robots in a very dense space to either avoid one another or chase the green ball while trying to avoid the red ball. And a lot of the problem with the adoption of continuous fiber composites, be it AFP or fiber placement or anything, is actually really, robots are incredibly difficult to program. They don't program themselves, and the consequences for doing this wrong can be quite dramatic. As you can see that robot freaking out there. So programming is challenging, and automatic robot programming is an even bigger problem. So here's robots with an objective. They're now have tools. They're taking turns, and they're trying to chase the green objective so that they can 3D print, but they still have to deal with the avoidance of the red ball. And so what we've started to create then is a modular structure to hold the robots, modular end effectors that work with a variety of chemistries, but then also a modular software package that can start to provide valid solutions for robotic tool pathing and so forth. Lots of dancing going on as it tries to avoid colliding with something that could be dangerous. So if the robot's actually 3D printing and interrupting itself to avoid somebody walking through the work cell, that's the kind of technology we need here. So here we have some robot prints that we did. This is actually a drone. On my screen, I'm actually holding the drone. You can kind of see it here. It's about 1.5 meter wingspan. We're targeting about, well, it should break 100 miles an hour quite easily. It's basically a quad rotor drone, but we're showing that the thermoplastics can actually be printed in various orientations on the same component. Another advanced software feature is being able to recover the builds wherever they fail. So if you're going to print a wind turbine blade that weighs 70,000 pounds and is 100 meters long, and one of the fibers breaks in the middle of the print, the computer needs to fix it. And that's kind of what we're showing here. That's why I left the defect. And here's, you can see actually with the 1 cubic millimeters, we have plastic aligned with the X vector, the Y vector, and the Z vector sort of all at the same time. Oh, let me, yeah, so the X vector here, the Y vector there, and the Z vector here are all combined in this one welded region of the part. So delamination now is not going to happen. Okay, and here's, yeah, just sort of completing this. Additionally, we need to have surface conformal overprinting. This means that, we need to not just think about 3D printing bricks, but also need to think about printing onto surfaces, regardless of how curved they are. And this is one of the advantages of robot printing over gantries. It's also interesting to note that robots are actually quite cost effective for the volume that they can print inside. They give you a lot of value in your sort of how big a robot you need to buy versus the size of the part you can make. Gantries are actually less cost effective than robots. So, and this is an example of how, excuse me. I'd like to show you a 12-axis print. This is zoomed into the part we're actually doing you could call it filament winding if you want to, but some of the maneuvers the fiber is doing, which is unsupported 180-degree turns and pivoting in place and stuff, you don't really do with filament winding, but you can think of it as a combination of printing on a surface and winding if you'd like. This is a 3D printed shoe. It is also scanned from your cell phone, and then you can make the shoe. So there's a lot of software that needs to be done in order to produce low-cost parts with robots. So this is sort of what a 12-axis print would look like. And really, one of the big ideas we want to show is that we've done a good job getting these little robots to print. They're going to be used quite heavily later in the presentation, but everything I'm showing you this is real, and we actually have products that we're selling based upon this technology. This is a different idea. How do you go faster when you start printing big things? Bigger nozzles don't necessarily mean better parts. They mean faster, but they don't mean more precise. So multiple nozzles attached to a single robot for parallel 3D printing is a very good idea, especially when you're building large and flat structures like fuselages and wind turbine blades. You can have a massively parallel print head such as this one. Let's go ahead and take a look at what that system looks like here. This is also a satellite, but just focusing on the parallel tool head for a moment. So this is a shipping container. We've got the robot comes out, a 5x5 grid of fiber layup tools, very low cost to operate system, lots of redundancy. There it is. So when the shipping containers are a notion also of scale, how we can make big things. Big cylinders are good, but how big? Let's take another look. So this yellow structure here is the bulbous bow of a full-size container vessel in dry dock. And so being able to print larger things like this to compete with heavy steel components is a great application for these technologies. So big is good, but it's not necessarily the most important thing. We need to have large robots, but we also need to think about fine details. So there's a lot of fine work in wind turbine blades, such as lightning strike protection. You might want to lay copper wires everywhere for grounding planes and things like that. So big robots are also a little wobbly and less precise than very small robots. So then we basically use, much like your hand has fingers, small robots to print with fine detail and elegant motion, and then we use big robots to fly them around. So big robots motion platform. And that sort of starts to look like this. This is a system that we're currently building and quite excited to use. It's a 5-meter robot. It's absolutely massive. And it allows us to deposit thermosets, thermoplastics, and continuous fibers with a lot of dexterity to print on the surface so that we can build things like this wing here. This is just what would be the wingtip off of a wind turbine blade. And this is exactly the kind of thing that a robot like that can do. But instead, now you're talking at much longer than 1 meter. So here we've got the small robots again. And let's go ahead and see what the fractal robots start to look like. And we can think of this sort of as like a hand. We've got fingers and an arm. So this allows us to go ahead and move around, change the shape of the end effector, and then also sort of have a very multi-material capable system. Very modular. In the case of satellites, you can use this hand to grab a satellite, just as you could use the individual fingers to refuel, repair, and manufacture off-world. We see a great convergence between these technologies. So here's one of my last slides, I guess. And this is sort of our view of how we think offshore wind turbine manufacturing is going to look like pretty soon. So all the robot systems we've seen before, this is actually just a 1-to-1 scale shipping container vessel, and they're absolutely massive. They're like 160 meters long and totally capable of producing one of these large blades on deck. So some of the challenges that we've showed before with the robots needing to avoid each other, the robots needing to be given specific tasks and avoid collisions with random objects, recover build failures and all of that is really critical to sort of get into one scalable system. So there's a tremendous software challenge, networking challenge, as well as chemistry challenges in order to get this whole thing to work quite well. But that's sort of what we've been tasked to do, thanks to the US Department of Energy. And yeah, we're, I guess, embarking on a journey to 3D print these mega large blades in a cost-effective way. And we feel that the mobile manufacturing is the same thing we want to send off world, but exactly what we would use inside of a car factory, because we're at the correct price point. So again, you're looking at an adaptable automated system that can go ahead and deploy continuous carbon fiber at very large scales, recover build failures, and also be mobilized. Those are all the requirements we feel that are in the way so that thermoplastics can be adopted by the wind turbine industry. If thermoplastics are adopted by the wind turbine industry, then the value of that for everyone else will be that a fully automated thermoplastic 3D printing system will become available at the correct speed and price point for potentially the automotive markets as well as traditional aerospace. So this is sort of how we feel the wind turbine industry will develop a technology that will change the rest of sort of manufacturing technology around the world. And this mobility is, again, the key aspect to producing wind turbine blades of ever larger scales for terrestrial wind. So yeah, that's really what we do here, and sort of yeah, I'd like to thank you for your time. If there are any questions, I'd go ahead and like to field them in the chat or whatever. Thank you.
Thank you very much, Mr. Nielsen. Please allow me to check if there is any question or comments from the audience. 네, 혹시 질문이 있으시거나 코멘트가 있으신 분은 손을 들어주시면 저희가 마이크를 전달드리겠습니다. Is there any question or comment from the audience? Yes, we have a question. Please answer.
Hello. I wonder, making time you show us, which is scaled blade. I wonder the making time.
Oh, how long would it take to 3D print a large blade?
Yes.
Great question. Thank you. So for a large number of robots in parallel, such as on the container vessel like this, we originally calculated a system like this would be able to produce about a 70,000 pound, 100 meter rotor blade in about 16 hours. That would be how long it would take to deposit the material. And then we feel that a stressed skin design is the best. So we would have side A, the high pressure side, low pressure side, and then go ahead and glue those together. We feel that is the best technique for producing these blades on site today. But I would say we should be able to make one blade every 24 hours, including the consolidation and cure cycle bonding. So 1 day. The print time is about 16 hours.
Thank you.
Thank you for the answer. And is there any other question or comment from the audience? Since there's no further question, I'd like to thank Mr. Nielsen for your keynote speech. Ladies and gentlemen, please give him a big hand. 박수 한번 부탁드리겠습니다. And we will now have a startup booster ceremony organized by Kita. Please wait a second. We will begin at 11 a.m. 잠시만 기다려주시면 키타에서 진행하는 스타트업 부스터 세레모니가 11시부터 시작되겠습니다. 감사합니다.